Okay, here's our video on heat and heat transfer part 3. We're talking about heat and temperature. So let's just make sure we remember what heat is, right? Heat is the flow of thermal energy, and we said that in the previous videos also. Let's say it again, why not? So heat is the flow of thermal energy, and we talked about thermal energy in the last video, right? So let's just write it here. Heat is the flow of thermal energy. And again, thermal energy is part of kinetic energy. So kinetic energy, remember we talked about in the last video, there are different types of kinetic energy, and thermal energy is one part of it. So another name for thermal energy is heat energy, right? Or internal energy. So again, with kinetic energy, it's the energy of movement, and heat is the flow of thermal energy. All right, so let's get a clean page going. All right, let me just write this down again. Change the color. Change to blue. So again, with kinetic energy, and it's the energy of movement. Now, inside, the particles inside a substance are moving. So when they're moving faster, the faster they move, the more heat is produced. And I'm oversimplifying things here. The faster, we'll just say the atoms, the faster the atoms move, right, the hotter, the more heat, we'll put it that way, the more heat will flow. So if you think about a cup of tea or a cup of coffee or anything hot, cup of broth, whatever you want to have, right? The particles, the atoms, are moving very quickly. They're bumping into each other and creating enormous amounts of heat. And of course, heat is the flow of thermal energy. It does not mean, though, that a cup of tea has more thermal energy than an iceberg, and we talked about that. The more massive something is, the more thermal energy it has, but not necessarily the more heat it has. So let's draw another example that clear this out. So again, here's our tea. We did this in the last videos also. And we have a lot of fast movement of these particles. And of course, the heat is radiating out. Now, in a giant iceberg, right, the cup of tea, you wouldn't even see the cup of tea. So in an iceberg, it's more massive. More mass equals more thermal energy. But the atoms, even though there's more atoms, they're moving slower. So they're moving slower in an iceberg, and that way you don't feel the heat. Let's give another example of this. If we had, let's say, have a cup of cold water, and let's put a temperature gauge in there, and then we had a giant pool. Oh, not so giant, but bigger than that cup. We should make the cup smaller. Let's fix that. All right, so let's just say that's a cup of water near our pool, and we'll just use blue for the water. There's our water, and there's all the water in here. You get the picture. And we'll put a temperature gauge in there, and we're going to talk about temperature in a minute. So let's say now they both have the same temperature, which is possible. Let's say that it's at 20 degrees Celsius. That would be about 65 degrees Fahrenheit. Let's say that's the temperature in that water. And again, it would be also 65 degrees Fahrenheit in the pool, 20 degrees Celsius. Now that is, 65 may be comfortable, but not necessarily for going into a pool. So 65, make that 5 a little better there. So they have the same temperature. That means that the particles, we'll just say atoms, the atoms are moving at the same rate. They have to be moving at the same rate for them to have the same temperature. Now, one thing you should know about this, though, it takes much longer, and this is common sense, it will take much longer, takes much longer to heat up a larger surface, we'll say a larger area, or a larger volume. It's probably better, right? It takes much longer to heat up a larger area. Makes sense, right? There's much more atoms. So if we heated this pool up, it's going to take a long time to heat up. But if we heated this little cup of water, then it could heat up pretty quickly, right? So that makes sense on that. So when we're talking about heat and temperature, heat versus temperature, and we'll talk about temperature in 1 second. We measure heat in joules. And we measure temperature in Fahrenheit or Celsius, depending on where you are in the world. Most of the world uses Celsius. Or we use Kelvin in science a lot. Kelvin. And maybe we should just use it. Maybe we should write it like this. Just seems a little better to do it that way. Let's not do it that way. All right. So we have Celsius, Kelvin, and Fahrenheit. So, for example, in joules, let's just say 4.1 joules, right, of energy, just to get you a little understanding of how many joules you need here, are required. So 4.1 joules of energy are required to raise 1 milliliter of water, for example, by 1 degree. That's a lot of joules for 1 degree and 1 milliliter. So if we wanted to fill up a cup, let's say we had a cup of water, which let's say this cup is about 250 milliliters, you can imagine how many joules are required to heat this up to boiling. If we wanted to make it to a boiling point, and water boils at 100 degrees Celsius. So in order to do that, if you do the math, you'd come up with over 82,000 joules, or 82 kilojoules, right? Kilojoules. So you need 82,000 joules to heat a cup of water to boiling point. Just to get you understanding what joules are. So again, we measure heat in joules, but we measure temperature in Celsius, in Kelvin, and in Fahrenheit. So let's go over that, clear that out. Last video we talked about absolute zero. And even though in the last video I said it's when all the atoms stop, it's not exactly that way. So basically, when nothing is moving, when nothing moves, theoretically you can reach absolute zero, right? Which is 0 degrees Kelvin, negative 459 degrees Fahrenheit, a little over that, and about 73 degrees Celsius, a little over that too. Now, the thing is, it doesn't actually happen that way. But for basic purposes, when we're teaching, we say absolute zero is when no atoms are moving. So we have atoms moving in the T, moving all over the place, creating a lot of heat. But in absolute zero, nothing will be moving. They'll be just still. But that is not exactly what's happening. There's something called the Heisenberg uncertainty principle, and I'm not going to go deep into it, but let me just type that out for you. All right, here it is. And we'll do it slowly. So the Heisenberg uncertainty principle, and it's reading it right there. Let's read it together. It states that there is a limit to the accuracy of the measurement of this blah, 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 right? So let's just, in other words, the more we know about a particle's position. So the more we know about a particle's position, the less we know of its momentum. So if we know its position, right, we shouldn't know its momentum. I'm going to talk about this in a minute. Let's go back to the other part. All right. So if we know its position, say we know its position, we're going to know less of its momentum. If we know its momentum, we're going to know less of its position. So that's basically what the Heisenberg uncertainty principle states. So if in absolute zero, when we used to say that everything stopped, if it stopped, we know its position. And if we know its position, then we would not know its momentum. Clearly, that's what it's stating. We're going to talk more about this in later videos. But I was just clearing up absolute zero. But for now, basically, when you get to almost where the particles are stopping or they're not moving fast enough, you can reach absolute zero, which is 0 degrees Kelvin. All right, let's move on. All right, so this came up before. So remember, heat does move to cold. That's a really important fact to know. Heat will move toward cold. When you touch something, for example, and you touch a surface, the heat from your body is actually leaving the surface, and you can feel that piece of metal, for example, might feel cold because metal does conduct heat better. So when you touch, let's say you're touching your locker at school, you just put your hand on your locker. Let's get our pen going here. And here's your hand, right? It's a nice hand, right? Got a nice little Apple Watch, whatever. And you touch this piece of metal, and the metal's going to conduct the heat better. It's drawing the heat away from your hand, and that's why you feel cold. But heat will move toward cold. Remember that. Another thing to remember about heat is less dense than cold. And we will do experiments. We have done experiments to prove that. For example, we know that heat rises, right? So when we talked about the sun, got our pen going here again. When the rays of the sun, the light energy hit the surface, it was absorbed, and then we had thermal energy being reflected, right? That thermal energy. We had the light energy, and we talked about this in the last video. It was absorbed and reflected as heat energy, which we know is thermal energy, right? But the heat will rise. Heat does rise. I'm sure we remember that. We know that. We probably learned that since 5th grade, perhaps. So if we took and we've done this experiment, and if you haven't seen this experiment, be careful when you do something like this. So if this was hot water, let's say that was hot water, the hot water would not sink into the cold water because it's less dense. But if you did it the other way around, the hot water will rise. So if you made this a red dye, and this was, let's say, a blue dye, get our blue pen here. This was a blue dye, they wouldn't mix if the hot was on top. The hot water was on top, but they would mix if the hot water was on the bottom. They would just mix. Getting to temperature, again, thermal energy is the flow. The flow of thermal energy is heat. We've said that a few times. We should know that. Temperature is not scientifically to say how hot or cold something is, but that's a basic idea. We know how hot or how cold something is. We can't just say it's how hot something is. Well, but we'll just leave it as how hot or cold an object can be. But scientifically, it's the average kinetic energy of a substance. It's the average kinetic energy of a substance. The average kinetic energy of a substance. And we use them, like Celsius, Fahrenheit, and Kelvin. All right, so I'm sure I don't have to explain what this device is to measure. So we have Celsius and Fahrenheit on one side. We just don't have Kelvin over here. But like we said previously, and let's get that pen. Remove this liquid. It's actually alcohol. It's not mercury. They haven't used mercury in a long, long time in schools. Because mercury, by the way, is not red. Mercury is a silver metal, but we'll talk about that in other videos. So if we got to, let's say, way over here, 100 degrees, let's pretend that's 100 degrees Celsius. That's boiling water. And we already said that it takes about 82,000 joules to reach that. So we can say that temperature, again, is the average kinetic energy, right? The average kinetic energy, and the average kinetic energy will tell us, will be converted in a way to what we think that would be in different degrees, whether it's Fahrenheit or Celsius. So it's the average kinetic energy. In this case, 100 degrees Celsius would give us about 82,000 joules in one sense. Let's review now. We know that heat is the flow of thermal energy. Heat moves from hot to cold. Heat is less dense than cold. We know that heat is measured in joules. We know that temperature is measured in Celsius, Fahrenheit, and Kelvin. We know that absolute zero is not exactly when everything stops moving, but for now, we'll just keep it that way. There is a principle, the Heisenberg uncertainty principle, that says that the more we know of a particle's position, the less we're going to know of its momentum. So if I knew that this particle was over here, I shouldn't know its speed. That's basically what it's saying. And in later videos, we'll talk about 0-point energy, which really talks about that even with 0-point energy, there could be energy. There is some energy, even if all the energy has been removed, which is very hard to understand right now. All right, so we'll continue with heat and heat transfer in our next video.